Good afternoon, ladies and gentlemen. I am Aniket from EDS Technologies and I will be your host for today's webinar. First of all, we thanks each and everyone for taking out time and joining the webinar, Shaping the Future of Automotive Lighting with Advanced Simulations. Before starting with our sessions today, I would like to give a brief about EDS Technologies. So EDS Technologies was incorporated in 1994 to focus on providing PLM solutions, implementation, and support. We are the largest technology solution provider in India and a platinum partner to Dassault Systems. We serve more than 2,000 customers and operate across 11 locations in India with our headquarters at Bangalore. We also have various strategic partnerships with other leaders like EOS and Optomec for additive manufacturing, Humanetics for ergonomic solutions for automotive and aerospace industries, Technia for ensuring product data quality. For military simulations and training needs of aerospace and defense industry, we have MAC technology, SLM technology, and AGM for visual simulation solutions. We also have a strategic partnership with Esri for GIS and location analytics. With respect to EDA, we closely work with Synopsys. We have a dedicated sales, marketing, customer satisfaction team to address customer PLM business and support requirement. Now we will move to our presentations. Before that, I would like to introduce to our technical speaker, Mr. Morgan Lu. Morgan Lu is a senior application engineer at Synopsys, specialized in lighting design and simulations. With 8 years of experience in customer support and training for light tools and Lucid Shape software, he has a deep understanding of optical system development. Morgan holds a master's degree in physics from National Yang Ming Chiao Tung University. So over to you, Morgan.
Okay, so can you see my screen now?
Yes, your screen is visible to us.
Okay. So hello everyone, I'm Morgan, and thank you for the introduction. And basically, I'm the leadership engineer in Synopsys. So today I'm prepared to know topic. First one is how to design the matrix bin system with our OSG tools, and the other one is the pixel light system. So we will introduce two different HLM type and show you how to use the OSG products to solve kind of this system. So let's start with the matrix bin. Okay, so first I will give you some introduction about what is a matrix bin, and then show you some design concept like how you define your target, how you build up your maybe reflector system or lens system, and then try to develop your system and do the analysis. And at least I will give you some summary. Okay, so in the introduction, basically for the matrix bin, okay, maybe I need to shift. Oh, sorry. Okay. Oh, sorry. So for the matrix bin, basically is one of the what we call the AFS system. AFS system means adaptive front lighting systems. So it's a new type of headlamp, and I think the basic concept is we just separate the whole headlamp module into the multiple bins, and we try to control the maybe turn on and turn off each bin, try to control the rate distribution, and for that it can improve maybe the safety or improve improve the driving safety for your car or for your headlamp. So the principle is for the matrix bin system, basically it will include maybe 10 to 30 vertical elements like as you can see here. For each bin, it will cover specific regions. So in this case, I think it's just maybe 15 bins in this system. So with this system, once you turn off some regions, and you can see here, this region will be dark. So we'll try to control bins individually, and with that you can control the light distribution. And of course, in this kind of a system, you must have some detector, right? So here, of course, you will include a detector system, and once for the detector, it will recognize, okay, there's car from the other side. So how many pins or which pins I should turn off. And then once this car passes through your cars, and then the pins will be turned on again. And for the ADB system, I mean the matrix pin system. So for the ADB system, first it's not just control rate distribution, but also give you a wider light distribution or brighter distribution. So for this picture, this one, or maybe I should turn on my laser point. So for this picture is a classic high beam design. So you can see the distribution is narrower and the power is not enough. So for the metric bin system, because I have used multiple pins, so of course I can get a brighter distribution, and of course I can get a wider distribution. Okay, so for the metric beam, what is the advantages of the metric beam? First one is I can give a far illumination, wide, high illumination. So you can get a better illumination, but the challenge is it will be more difficult to design it because you have to control the tolerance. You have a lot of components, and then of course you will have a big size of your headlamp. So here is all of our challenges. So of course we have an advantage, but we also have the challenges. Okay, so the next step is I'm going to introduce some design concept about the matrix bin system. So first one, this one is from the Audi, and for the Audi, this kind of system it uses the reflector as the bin shape. So here you can see it's used the 5 reflector, and for each reflector it represents the bin. And in this picture, you can see he used 5 pins, and then you also will have some other system like maybe the mechanical parts or low beam parts or something else. So here is the full system, and for this one, and for the matrix beam, it will control the high. It will reflect the high beam system. And this one is the close-up image. So here you can see we use the in the Audi, it's used the 5 pins to control the rate distribution. And this one is another design is from the Hella. So in the Hella's design, it's used the 10 pins to do the. It's also used the reflector system, but it's used the 10 pins to control the rate distribution. So you can get more more high resolution result. And this one is for the projector lens. So for the previous one, and I mean for the previous 2, and for the Audi and the Hella, they use the reflector as their matrix beam system. And this one is use the projector. So projector means it will use some lens module to project their light ray distribution. So here you can see here it will include some lens system, and it will also include some illumination system. So with kind of this design, as you can see here, we have a LED array here, and then this one is some collimator. So basically, it will try to reshaping your ray distribution, and then reshaping your pins, and then use this lens to project the ray on the road. So basically, if you want to design some collimator, you can try to use the Lucy Shaper or use the illumination tool to do like Lucy Shaper or Lucy Shaper CA to design it. But if you want to design the projection lens, you have to use some imaging tools such as like Ko-Fi. And in the next session, in the next topic, I will introduce the pixel light, and pixel light is the imaging system. So in this case, we will try to use the Ko-Fi to design it. But in the matrix beam, we just use the Lucy shape. Okay, and next step is development. So how we can use the Lucy shape to in the matrix beam design. So first one, we will try to use an LID editor. LID is means light intensity distribution. So basically, for each pin, it will be the single distribution, right? So first, you have to combine all of this distribution and try to check maybe check the specification or regulation or something else. So you have to check it. And also, you also can try to use an LID editor to define your target. Like, okay, maybe I want my light distribution is from maybe horizontal is 5 degree and the vertical direction is 10 degree. And I want to check maybe 10 pins distribution with this condition, or I can switch it to another distribution or another condition to try to get a different light distribution. So you can use this utility or use this tool to make any distribution you want and try to check your result. So in this picture, you can see we can add multiple bins. So first one, we have a low bin, and we have another bins, and I mean the ADB matrix bins. So you can import a lot of different bins and try to check the arrangement, try to check the power, or try to rotate it or something else. Okay, so this one is some foundation for the high bin. So here is for the low bin. So here you can see here is a low bin distribution. So it means this one. So you will have a low bin distribution first. And then this one is a classical high bin distribution. And now we want to use the matrix bin to replace the high bin system. So first, we use the macrofocal feature. Macrofocal feature is a really powerful feature in the leadership. So basically, you can just define your rate distribution. So for example, you can just define, okay, I want to get a uniform distribution in maybe a horizontal direction is 5 degree and the vertical direction is 10 degree. You can just define this target, and the leadership can help you to compute the shape of your reflector or of your lens and try to achieve your target. So you can try to design a single beam first, and then we'll try to do some arrangement, we'll try to do some shift, and to check the result. So first of all, first step, we use the macrofocal to design the first beam, and then we try to modify it. So here you can see the horizontal direction is around maybe, I think this one is 5 degree, for the vertical direction is around maybe close to 10 degree. Okay, and here is some projection view. Here for the bottom picture is the far field view, and for the top picture is for the driver view. So you can check for the single beam, you can check the projection results on the road or in the far field receiver. Okay, so in the next step, I will import the list bins and combine with my low bin distribution. So here you can see I just imported the 2 bins in this system. So you can see the combination of these two light distribution. And then you can try to import multiple bins because in this case, I think we will use maybe 8 bin or 10 bins. So you can import different bins. So here you can see I imported 2 bins, and you can just change the position or change you can shift it to check the distribution. And then here is the different the position. So here you can see if you have for the position one, you can see you will have some dark line between these two high bins between these 2 bins. But if you just modify it, you can see here is the dark line is disappeared. So you can try to control your coordinate and try to solve the dark line issue. And here we import the 10 bins. So one is low bin, and for the rest of part are the high bin system. So we use all of these bins, and here is this picture is when you turn on all the bins, the result. So after the analysis, so as you can see, we just can combine. You can save this result as your maybe the target, or save this result to do some to test the regulation or something else. So we save this result and we just project try to check the color view and try to check the driver view to see the light distribution and the color performance. And this one is the bird's eye view, I mean the top view. So again, you can just save your result and import it to the loose shape or import it to our we have a utility called advanced analysis. It is an analysis tool. So you can try to analyze your result in this tool. So you can see here is the top view, and here again, this one is the color view. Okay, so for the LID editor, basically you can just import any bins you want, and you can try to move it. You can try to rotate it, scale it, and to check the different light distribution. And once you finish your modification, you can save it and try to apply it in the maybe driver view, color view, or bird's eye view to check the performance of this whole bin system. And next step is go to the macrofocal designs. So for the matrix bin, basically it will follow some, you can use we will use the macrofocal feature to design it. And actually in this example, we will use the macrofocal reflector. We will try to design a reflector system. So we will use a reflector to design it. So first, as I mentioned, you can try to try to design a single bin and then just copy it. And then try to copy it and make some array, and then you can get the light distribution. Okay, so here is our macrofocal reflector models. So first one, you can just define some light distribution. So here is for each macrofocal reflector, we have 3 phases. So for each phase, you can define different light distribution, and Lucius can help you to compute the shape of the surface and try to achieve your distribution. And in the previous slide, we already used the LID editor. So we already know the coordinate, or we already know the location of each bins. So that means you can just apply the list location in different macrofocal reflector. So with that, you can easily to get, okay, so if I want to shift 5 millimeter, or shift 10 millimeter, so of course your bin distribution should be shifted as well. So in this case, we already get all the information from the LID editor, so we can just apply it in the macrofocal reflector. And you can just use a copy and paste, I mean Control C and Control V, and to copy your array and try to modify the position, modify the array distribution, and get the result you want. So here is the 10 bin system. So for the top 5 and the bottom 5, so we totally have the 10 bins. And here is the full model for the high bin module. And this one is a high bin module, and this one is for the low bin. And for the low bin module, again, we also use the macrofocal to design it. You can use, for example, in this case, I think it uses the 9 phase to design the low bin distribution. So here you can use here is the 7 phase. So use a 7 phase to design the low bin distribution. And then here is the visualization result. So as you can see, so now we will use the high bin. High bin is this part, and the low bin is this part. So basically, you can try to use a model, and in this case, we just use the reflector as our design system. But actually, you try to use maybe the macrofocal lens features to design the lens array, and try to get a different distribution. But the design concepts are same. So first, you have to define your distribution. I mean your target, and then you can change the position of each macrofocal reflector, and Lucius can help you to design the shape of your reflector and lens and try to achieve your target. And the next step is for the analysis. So for the analysis, the first one we always Actually, in the previous slide, I already showed some driver view or bird's eye view, and there's some analysis we want. But we also will try to do some another analysis, like we will try to pass the regulation, or we try to get some different view, or try to consider different condition or something else. So here we also have some utility can help you to do analysis. So first one, of course, is regulation. So for the regulation, we have we call the test table. So in the test table, you can just apply to your the regulation, and the Luship can help you to do an analysis and show you, okay, if your distribution is passed or not. And here is again, here is a driver view, so you can check the driver view of your headlamp matrix spin distribution. Or you can use some string luminance, like for the driver view, you can define the right, left hand lamp and the right lamp, and try to do some combination, and it can export the result for you. And again, you of course you can define maybe the driver position or the road size, and even like the field of view, something like this. So you can define every parameter, all of this parameter, and set it as you want. And this one is the bird's eye view. So again, you can define your position, you can define your distribution or something else, and try to get the bird's eye result. And this one is, I think this one is a new feature in the 2024. In last year, we just released a new feature in the Luship, and this one is called the FMVSS 108 ADB tools. So with this tool, because in currently, I think FMVSS 108 ADB tools is kind of the benchmark tools. So because we have a specific regulation, we have a specific specification. So we need to apply some different condition to test our headlamp. So if you want to analyze your headlamp with the FMVSS 108 regulation, you can try to use these tools. So here, as you can see, you can just define your headlamp, your light distribution, and you can define the regulation. Again, you can define some mask, the minimum and maximum size of your mask, and for the low beam part and for the high beam part. So you can define everything you want in this table or in this dialog. So here you can just once you finish your definition, you can just create the result LID. You can save it or show it. And then you can define the regulation. So here, as I mentioned, you can define the regulation for the low beam or for the high beam. So you can just, here is sent as our test table. So you can just collect it and select the regulation you want and apply it into this utility. And then this utility will follow all the definition and try to help you analyze your system or your headlamps. And again, it will show you, okay, if your result is passed or not. So here is we use the different color, different number to show you the result. So for the FMVSS 108 ADB in the loose shape, it is for the static simulation and then static analysis. And the other one is in the loose drive. So again, it is the same. I think it is pretty similar with the previous one. It's also called FMVSS 108 ADB tools, but this tool is in loose drive because we try to analyze some dynamic results. So we have some we can define the road condition like the curve, like how many car you want, and the sensor precision or something else. So it can, and once you finish all of this, actually we already have this. Yeah, we already have this in our loose driver tools utility in loose driver. So basically, you can just call this function and try to apply your headlamp into the model, and loose driver can start do the simulation and try to help you to get the result. So here is the specification in this regulation. So here you can see we define the different curve or deploy different maybe the car position and the sensor position. And once you turn on the simulation, so the car will move in and to get the result at a different point. And then it can help you to analyze to do some dynamic simulation, dynamic analysis. So here is a video. So maybe I can play it. So you can see here is the video in the Lush drive. So when you close to the other card, and you can see here is your energy curve. So here the green pointer is our sensor. So you can see it in the sense at the sensor, it can receive different values, and once it passes through the cars, the energy will drops down here. So with this feature, it can help you to do some dynamic analysis. And we also include some special scripts in the root drive. So in the root driver, once we already included some scripts, so all you need to do is you can just import your result, import your light distribution into the root drive, and just apply the different script, and then Lucia can help. Lucia will follow these conditions and try to do the dynamic analysis. And here is the top view. So as you can see, here is top view. So Lucia in the Lucia driver, it will recognize, okay, there's a car come from the other side. So when it detect it, and it will not turn off the view beams. And once when this car passes through your cars, and all of these beams will be turned on again. So you can see some video about your simulation result. And here is the driver view. Okay, so here's the summary. So basically, in the Lucy, for the matrix bin, we use the Lucy shape and the Lucy driver to do the simulation. So for the Lucy shape, we will use some, for example, like LID editor or like maybe the macrofocal reflector or macrofocal lens to design your element modules. And then once you finish your design, you can save the result and import it into the Lush driver. So in the Lush driver, you can do some dynamic simulation and to try to get some video about the result. So it means you can get some visualization result in the Lush driver. Okay, so I think that's first part about the matrix bin. So I think we can just go to the second part. So if you have any question, you can just ask it after my presentation. Okay, so for the next part is the pixel light. So for the pixel light, we actually use the Lucy shape, Lucy driver, and Copy. So why we use the Copy? Because for the pixel light system, in the matrix bin system, we just use maybe 10 to 30 bins in the element. But in the pixel light system, we usually will use over maybe 1,000 bins in this kind of this system. So that means you cannot just use a reflector to do it. You must use a lens, and in other words, you have to use you have to use the lens module, because because now your element is just like a projector. So projector is an imaging system. So of course you have to use the imaging tool to design element. So that's why we will introduce the Copy in the pixel light system. So okay. So again, I will try to give you some quick induction about the pixel light, and then we will show you how to design it in the Copy and how to simulate it in the Lush shape, and finally go to the Lush drive to check some visualization result. Okay, so first part is some introduction about the pixel light. So again, pixel light is one of, or maybe I have to turn on my last point again. So for the pixel light is kind of the AFS system. So adaptive front lighting system. So with this, sorry, with this purpose, and so pixel light can now control the bins and try to turn on and turn off again, and try to get a different distribution. The different thing is the only difference between the pixel light and the metric bin, I think, is the size or the pixel numbers. So as I mentioned, for the metric bin, we just use maybe 10 to 30 bins, but in the pixel light, we will use thousands of bins. So it will be more, complex system. So yeah, and we will have to combine it with the code file and try to design it. So here is some market opportunity. So that means some who will have an interest about the pixel light, like OEM, less manufacturers, source manufacturers, or lamp manufacturer, or something else. So you can see a lot of different different people in a different field. They are all have an interest in about the pixel light system. So this picture is pretty clear for what is a pixel light. So basically, we just pixelize our bins and try to control each bins to get a different light distribution. And because the resolution is pretty high, and so we just call it a pixel. It's not just the metric bin; it will be the pixelized system. And here is some example. And this one is the Mercedes E-Class. And I think here this one is more close to the matches bin, not the pixel light, because as you can see, it's using more bins. Because I think it's around maybe 30 bin or 40 bins for each headlamp. So yes, you can call it as a mattress bin, but I think the resolution is not very high. So if you want to, for this picture, this one is use some DMD system. So with this system, you can see it's just similar with the projector. So you can project any symbol you want. So because you have a highest resolution projector. So with this case, you will need to use a different design tools or use a different system to design it. Okay, so here is what we need in a pixel light. First one is the source. So for the source is the pixel light phosphorus source. So as you can see here, you can see a lot of pixel in this source, and you can just control it and try to turn on and turn off for each pixel to get a different distribution. Of course, you will have mechanical parts, like you will have PBS. PBS is bin splitter, or some maybe reflector, or some lens system, or some other mechanical part in your system, or like the LCD or LCOS system or something else. And this one is the DMD. DMD means the digital micro mirror device. So with this device, it can control for example, if your projector system is a DLP system or some I mean the DLP system, yes, maybe DLP system, just DLP system. So if your system is a DLP system, that means you need to use this DMD chip to control the light distribution and try to get a different result. And of course, we will have some scanning system like a laser. So for the scanning laser, can create an image, and once you rotate these mirrors, and you can get a different light distribution. So you will have a lot of different components. You will have the different requirements or something else. So it will be more complex. It will be more complex system if you compare with the matrix bin. Okay, in this case, we will use the LED, pixelized LED. So here, I think this one is, oh yes, here we mentioned it here. So with this LED is from the Osram. It's called the micro FS system. So with this LED, I think the resolution is 32 by 32 for single LED system, and we will use the multiple LED and the multiple modules to create the distribution. So here is in each module we call the pixel light module. In each module, we will apply the two LED. So that means we will totally have 32 by 32 is totally have 1024 pixels, and we will have two. So that means we will have 2048 pixels. And here is some specification of this pixel, like the pixel size is 115 micrometers, and the spacing is 10 micrometer, or the power and the total area or something else. You can just take a look about the specification of this LED. And then for each headlamp, we will include 2 modules, 2 pixel light module, and we have 4 headlamps. So totally for each headlamp, we will have 4,096 pixel in total. And for 2 headlamp, we totally will have close to the 8,000. And here is the lens system. In this case, actually, in this case, we will use the 4 lens system to design it. But actually, you can try to design your system with triple-8 lens. I mean, the 3 lens, or double lens, or like the single lens system. You can try to design any condition or any requirement you want. But if you use the more lens, that means you are increasing the flexible of your system. Because for the 4 lens system, you actually have a surface, so you can try to use the a surface to design your system, try to achieve your target. But if you use maybe the 2 lens system, that means you just have a 4 lens surface, so it will be more difficult than the 4 lens system. But if you increase your lens, that means you increasing the cost of your headlamp. So yes, we have to know. That depends on your requirement. It depends on your purpose. Okay, and here is some condition about our target. So first, we will try to get the horizontal range about maybe 32 degree, and for the vertical is 8 degree for each headlamp. And here is some angular resolution, and here is some illuminous target, and some other things. So you can just take a look, because for a different design or for a different designer, the design target may be different. So you can just take a look. Okay, and the next step is design workflow. So first part, we will design our lens system in the CodeFile. And once we finish the design in the CodeFile, we will export the lens model and import it into LucidShape. And in LucidShape, we'll do the system simulation, like apply the source array and try to analyze maybe the candela distribution or lux distribution or some other distribution you want. And the next, we will go to the Lucid driver to check the visualization result. Okay, so here is CodeFile. So again, as I mentioned, because we use a lot of pixels, so in this case, we totally use, for each headlamp, we use the 4,000 pixels. So with kind of this high resolution system, you have to use the imaging tool to design it. So how CodeFile can help? So first, you can just keep track of the performance and the specification and the goal during the design, and you can try to pick a good start point and optimize your system, and quickly learn about the tolerance or some possible assembly errors during the performance, and analyze your system. So in the previous slide, we already defined maybe the specification and maybe define the target. And then you have to go to the CodeFile to design your lens system and try to optimize it and export the result to the LucidShape. So here is the specification, and I already showed it in the previous slide, so you can just take a look. So for each headlamp, we have 2 modules. And 2 modules, and have 2 lens system, and with the 4 pixel light display. So here you can see we have a 4 source array here. And for the field of view of our headlamp is 32 degree by 8 degree. So for the half degree, for the semi FOV is 8 degree by 4 degree. And for each module, we have 2 display, one side by side, and the size is 4x4, and so totally is 4x8. And the pixel size is 150 micrometers, and the pitch is 125 micrometers. And when we design this kind of this system, we will use the diagonal direction in the code file, because we have a symmetry system, right? So you can just design a single direction. So here we just define the semi FOV is 90 degrees. So as in this picture, you can see we just define this direction, and we'll try to design this direction and try to get the best result. And here is some special concept in the imaging tools, like what is EFL, what is EPD. So you can just take a look, because this one is some popular wording or popular names in the imaging design. So EFL is effective focal length, and EPD is entrance pupil diameter, and the FOV is FOV of view, and is numerical apertures or something else. So you can just take a look, because in the latest slide we will have some talk about all of these parameters. Okay, so the first one is we have to design the first state of our the initial state or initial design of our system. And here in the code file, we already have a lot of libraries. So you can just choose one. So how we choose the library? So here we already know, or maybe go to this slide. Here we already know, okay, maybe the angles, like we want the distribution is 8 degree by 4 degree, or the resolution, or the source size. So you already have a kind of these parameters, and you will know, okay, maybe the size of your system, or maybe the width of your system. So you already have a kind of these parameters. So you can just use this parameter to filter the library. So here you can see, here we use the F number and the semi-field of view to filter the length. So here is the different, all of these lengths can achieve our conditions, and we just select one as our initial state. So here you can easily use the code file to determine your initial design. And then here is the imaging performance. So actually, for the code file, you can use two configurations to design your system. First one is from the roadway to the pixel display. So that means the design direction. So maybe I can use the pen to show you. This is my, oh, here. So the first one is, okay, when you decide the red direction is from the road to your source. That's the first one, and the other one is from the source to a road. And I think both are available in this system, but because at least we want to analyze some far-field distribution, we try to analyze the result on the road or something else. So with this condition, so in this case, we will try to design the system from the pixel display to a road. And then in this design, we will try to analyze the spot size, I mean the spot diagram, or the MTF, and some distortion. And all of this target is for the imaging target. Okay, so here is the starting system. So for the starting system, you can see F number is 1.2, and we will try to reduce this number. And here we set the surface parameters as a variable. So you can see the red B here. So for the red B is mean variable. So we just apply the parameter like thickness or like the radius as a variable. And then here is a spot diagram, and here is distortion, and here is the MTF. So all of these three, we will set all of these three as our target, and try to multiply the variable and to achieve our target. So in optimization, we will use some different functions. The first one is local optimization. So it can help you to get the local minimum very quick and very fast. But we also want to get the global result, global optimization result. So here you can switch to the global optimization engines. So with this engine, it can help you to find the global optimized result. And here is the glass expert. So with the glass expert, it can help you to decide the material of each lens, because the refractive index will influence your image quality. So of course you can try to use the Ko-Fi and use the glass expert to design your system. Try use this feature to decide which material is best for you. And then with in the image system, we always need to analyze the tolerance. Tolerance means if you have some like the position of each lens or curvature of each lens, if you have a little bit of shift of the position or have a little difference about the surface type, surface shape, it will influence your image quality. So you can use this feature, try to do the analysis and also do the optimization. Okay, so here is our design process. So first one is for a starting point, and then we will try to optimize it. And here is the optimized result. And then after that, we will analyze the spot diagram. So the spot diagram is pretty good. It's a bit smaller. And after we reduce the F number, you can see the power efficiency is increased. It's increasing. So the result is pretty good. And then we try to use the global optimization, try to get the global solutions. So here we use the global optimization and try to get the different results. So all of these 5 results can pass our requirement, can achieve our requirement. And you can just choose, okay, so here is the last result we choose. But you can see Ko-Fi can help us to get a different results. But for example, like this one, the lens one, the distance between the lens one and lens two is too small. So it may cause some issues when you try to manufacture it. So we don't choose this one. And again, this one it will have some weird shape, and it will be difficult to be manufactured. And same for same issue that will occur in these 2 results. So at least we try to we choose this result as our final design. And then this one is the glass expert. As I mentioned, you can just use it to apply it in your system, and this function can help you to choose the material of your lens module. So here it helps us to choose the different material and can achieve our requirement. And finally, here is our final result. So the size is by around maybe 50 millimeter by 40 millimeter. And here is the parameter of our lens. And here is the MTF, the distortion, and the spot diagram. You can see all the result can achieve our requirement. Okay, and here is some comparison between the first result and the last result. Okay, so here once you finish your design in the Ko-Fi, and then you can just export it as maybe the IGES file, set file, or step file, and then you can import it into the loose shape. So in the loose shape, here we will try to design maybe the source. We will build the source array. We will try to simulate the pixel light system, not just for the lens module, but also for with the mechanical parts. And then once you finish all of your simulation, you can save it as a LID file, I mean the light intensity distribution file, and you can import this file into the loose drive and to check some visualization results. So the next step is go to the loose drive, loose shape, and try to apply the source, sensor, and to do the analysis. So here is a model in the Illustrator. So we just import the CAD file into the Illustrator, and then we try to build a bitmap and try to create some imaging source to this system. So here we just use the source and reduce image to the 100 by 100 pixels and convert it to the light source. And with the pixel light source utility, first one you can define the number of your pixels. So here we use a 100 by 100. And you also can define the power of each pixel. So here we call the dimming matrix. So you can use the table to define the power of your pixels. And here is the position and the size of your source array. So once you finish your definition, you can just see here is a near field, here is the source side, and this picture is a far field result. So with this result, you can see a clear image here for the far field result. And we also try to use the doublet result. I mean the double lens system. So you can see if you use a double lens system, you will see some blower effect. So that means the resolution will be low. That is because you just use a two lens. As I mentioned, if you use a four lens, that means you increase the flexibility of your system, so it will be easier for you to get a perfect result. But if you reduce the lens, it will cause some blower effect, and that means your resolution will be decreased. And the next step is in the Illustrator, we can define the source array, and we also can get the result for each pixel. So for example, in this picture, maybe it's use 100 by 100 pixels, but we can check the result from each pixels. Like here, you can see here, we check the 5 different pixels. Maybe in the next slide, oh, this slide is more clear. So for example, the next pixel is at the corner, and you can see the straight line or result is different between the corner and the center. So with the loop shape, you can just save all the result of each pixels, and you can just turn on and turn off it, and then try to analyze the distribution for the result of the ghost and the straight line. And here is the Y image result. So we just input the Y image, and here is the far field result. This one is a 3D LID mapper. So for the previous slide, we use the pixel light source, or maybe this one. We use the pixel light source to define the resolution, to define the power of each source and the position and something else. But sometimes we just want to do some quick check, like, okay, I already know the contribution of each source, like this picture. So here we already know the contribution of each pixel or of each source. Can I just modify the result and try to regenerate a new result for me? So with this mask, I don't need to rerun the simulation. So yes, in Illustrator we can do it. So here is you can use the matrix to define the power of each pixel. I mean the pixel is the result, pixel on the result. So you can define use the max to define the power of each pixel, and then just apply it into our original result. And then with that you can get the new result, and this result will be much faster if you compare with the original math. So here you can see here the provided source flux multiplication in post processing is just maybe 200 milliseconds. So it will be much faster for you. So it can help you to save the hundreds of hours of the simulation time. So with this utility, you can just define first you have to define your LID file. So you can just import your LID file and then define the map distribution, like it will recognize your source. For example, in this case, we use the 100 by 100 pixels. So here you can see here it will recognize your pixel numbers, and you can define you can do some modification here, and you also can do the mask, like as I mentioned, you can define maybe the power of each pixel or the energy of each pixel and try to get a different distribution. And then click on the right, so it will overwrite your original result and to get a new distribution. So here is the list result, so you don't have to rerun the simulation, and you can just get the result very quick. Okay, and the next step is the loose drive for the visualization. So in the loose drive, first is here's some quick introduction about the CRT ARC. So this is use the loose shape and the loose drive as a regulation validation. So for the loose drive, again, it's pretty similar with the matrix bin. So we already have some scripts. So you can just apply this script and import your result. So when the loose drive detect a layer here is cut, so it will turn off the bins and try to don't blind the drivers from the other side. And then once this car passes through your cars, and all of the bins will be turned on again. So for the visualization workflow is once you finish your design, and you can save your results as a RID file and then import it into a loose drive, and you can just apply the script, or you can do programming your own script and try to get a simulation. And we just do some dynamic simulation, so it's around real-time visualization, and you also can change your views for the analysis. So here is some test results. So here is, you can see, we just turn off these regions, and the area behind this region will be black. So it will turn to the dark area. Try to don't blind the driver from the other side. And here is some picture result. And here is the wall view. We just place the wall in front of the car and try to make the user can check the distribution on the wall. And here is the distribution on the road and on the wall. Okay, so here is the conclusion. So basically, in this pixel-like case, we use the co-file loose shape and the loose driver to design this case. So for the co-file, we use it to design the lens module. And for loose shape, we will apply the source sensor and the whole system to analyze the performance in the system level. And at last, we will save all the results into the loose driver and try to do some visualization, try to do some dynamic simulation. Okay, so I think that's all.
So now I would like to thank Mr. Morgan for delivering a very insightful webinar today. And I'm very confident it was very helpful for our audience today. I also would like to thank our audience for taking their time out and joining these sessions. If you have any further queries related to subject matter or any other requirement, you can always connect with us. Our details are displayed on the screen right now. You can reach out to us at any time, and we would be happy to address your queries. Please do keep an eye on our upcoming seminars and webinars. You can follow us on our social media platform for the same. Okay, thank you, everyone.
Okay, thank
Thank
you.
you, Morgan.
Bye. Thank you. Bye.
Bye.